Welcome back, class, to Introduction to Material Science and Engineering. We've covered several topics in the class so far about material selection, structure of materials, and probably even touched on just a bit of material processing. And now we're going to kind of turn the tables and look at all of the things that can happen to undo our good work once we put materials into service and address the subject of material degradation. May not be quite as positive a subject as building materials and understanding their structure, but it's certainly probably as or more important in knowing what to select or not select and how to deploy things properly and safely. So we're going to address three different topics under the general heading of material degradation. The biggest one will be electrochemical corrosion, which is unique to metals, although variations of it can occur in other materials. The high electrical conductivity of metals supports this fairly unique and rather pervasive type of degradation. We'll touch on chemical degradation as opposed to electrochemical, and because it doesn't require electrical conductivity, it can affect anything. Most importantly, we'll address polymer solvent swelling, since that controls selection of polymer materials for a lot of the applications in which they're uniquely well suited. And then we'll touch on, just very, very briefly, high temperature gas reactions in ceramics, perhaps just in passing. These have analogs to both electrochemical and chemical degradation of other materials, but is unique to the high temperature environments in which we would find a lot of ceramics, turbines for power generation, refractory applications in furnaces, etc. We'll give a little bit of mention to photodegradation of polymers, especially because that is, again, like electrochemical corrosion for metals. It's something unique to that material family. And because polymers are frequently used in outdoor applications, mainly because of their electrochemical corrosion resistance. And their very poor resistance to photodegradation is frequently ignored. And that's something that definitely needs to be considered for weathering applications outdoors. Okay, the electrochemical and chemical aspects of material degradation spawns its own set of terminology, not surprisingly. So we're going to have to go over quite a bit of vocabulary in reference especially to electrochemical corrosion of metals. But these are very, very similar to the types of energy and thermodynamic terms that we've already touched on in this course, specifically with reference to interatomic spacing, diffusion rates, and the energy necessary to form surfaces, and the strain energy associated with lattices that will drive recrystallization and phase changes. This is just a different type of energy, namely that uniquely associated with chemical bonds and charge transfer. So, reaction potentials, first concept. Chemical reactions are associated with changes in system energy, just like just about everything else in material science. So if we are at constant temperature and pressure, two state variables, and that will be frequently the case operating at the Earth's surfaces in engineering applications, the direction of spontaneous change of a system is given by what's called the Gibbs free energy. This will be the case for the spontaneous direction of a chemical reaction, because that is a system change. So a chemical reaction or an electrochemical reaction, if we have a metal corroding, will occur if the sum of the free energy of the products is less than the sum of the free energy of the reactants. So we have a reduction in overall system energy. This is not a new concept. We've touched on this, again, in several different respects in the class, so this is simply applying that same overall system energy reduction to chemical reactions that might be involved in corrosion or other type of material degradation. So if our delta G of reaction is negative, the reaction is thermodynamically possible and could happen if it's not kinetically limited. If you have charged species, we need to account for the fact that we've got changes in electrostatic energy of the reactants and products. So we kind of have two things going on there. We have the free energy change of just the rearrangement of the chemical bonds, and then we have the rearrangement of uniquely charged species like ions and free electrons that need to be taken into account. So we can lump those together and have a term that's called a reaction potential, which accounts for both the electrostatic character and just the plain old chemical character. And if we're talking about a reaction proceeding, we could look at the change in reaction potential as being the minus, the negative, of the number of electrons involved in the reaction times Faraday's constant, which is literally the charge on 1 mole of electrons, times the delta G of reaction. So now we have a single term that involves anything that's involved in the free energy change involved with an electrochemical reaction. So that brings us to the concept of a half-cell potential. So if we can define the electrochemical potential of a species or a single reaction, we should be able to look at half of that, something gaining or losing electrons, and assign a delta E of reaction to just that one-way direction. So again, we can apply that to one side of a chemical reaction involving charged species. Now, if you're familiar with chemical reactions, if you've taken some chemistry, you might have run across the concept of a standard state, standard conditions that you would look at free energies of reactions under those conditions. We define in electrochemistry and in corrosion a standard potential, which is an analog to this, and all it means is that we have defined some of the thermodynamic state variables involved in the reaction that's going on, namely pressure. So we assume that we have 1 atmosphere of pressure. We assume we have 1 molar concentration of any of our dissolved species, and typically we'll define also room temperature, 298 Kelvin. So this just gives us sort of a benchmark for comparison, because as we start looking at changes in our half-cell and cell potentials, we'll be looking at the effect of increasing or decreasing concentration, and we'll try to rank which reactions are more favorable if we have the possibility of several going on at one time. So by defining a standard potential, we kind of have a level playing field of comparison, and that's why that concept is used. And most of these are defined, they're in handbooks, you can look them up, and then you can use them as part of the basis of comparison to conditions that might not be at standard state. So we'll see how that works out with some equations later on. So we arbitrarily define special reactions as having a defined half-cell standard potential, and that reaction is reduction of hydrogen ions to hydrogen gas with 1 molar concentration of hydrogen ions and 1 atmosphere pressure of the hydrogen gas. This is called, actually, if you build this electrode, physically build it, you'll have something called a standard hydrogen electrode, which goes under the acronym of SHE, and this is defined as having a standard potential of 0 volts. So this is just, again, it's just a benchmark to use for numerical comparison of other reactions. There isn't anything absolute about that 0 volts. But having defined it at 0 volts, we can now rank other things, and that's where things become really useful. For instance, we can look at the standard potential for reduction of silver ions to silver metal and see that that has a standard potential of almost 0.8 volts versus the standard hydrogen electrode. Zinc is completely at the other end. It's more active. So in order to reduce zinc ions to zinc metal, we would see that that reaction has a standard potential of negative 0.763 volts versus the standard hydrogen electrode. And if we look at two dissolved species, which we can frequently encounter in corrosion of steels, ferric ions to ferrous ions, the Fe3 plus to Fe2 plus, if we're going to reduce Fe3 to Fe2 by adding an electron to it, to that ion in solution and getting another solution ion, that occurs at a potential right around the same potential we would have to reduce silver ions to silver metal. Coincidentally, they're not related per se, but that's 0.771 volts versus SHE, our standard hydrogen electrode. So if we looked at a whole bunch of different reactions that might be of interest to us, we could rank all of them in terms of the standard electrode potential for each of the reactions, and of course this requires that all of these reactions be occurring at standard conditions. All of those solution species are present in 1 molar concentration. You have 298 Kelvin temperature for all of them, and if there's any gas species, they're present at 1 atmosphere pressure. So this gives you an idea of what types of species like to gain electrons and what types of species like to lose electrons. Just gives you a general ranking of what is more noble, things that like to gain electrons, like gold up at the top, versus things that like to lose electrons, like sodium down at the bottom. And it is not surprising that this should follow your electronegativity trends that you saw in the periodic table back at the very beginning of the course. Unfortunately, for practical applications, it's not so interesting because very, very rarely do we work out in the field in real conditions at standard conditions. So you won't typically encounter 1 molar concentration of lead ions, or at least hopefully not too often outside of the laboratory. And most things of interest don't necessarily happen at room temperature. So we need to have other ways of adjusting this to more real conditions to get some comparisons. Now, something to remember stepping ahead from the idea of half cells is we haven't really completed a circuit. When we look at half cell potentials, we are looking at only 1/2 of a reaction. So you'll notice on the previous slide that we've only been looking at reduction reactions, or the free energy change and associated potential change to add an electron to something. And we've shown that it's very easy to add electrons to ionic species that are noble, and more difficult to add them to things that are active down there at the bottom of the EMF series. But in real reactions, those electrons have to go somewhere. So we have to have a reaction that's going to give up and release electrons, as well as one that will accept them. So in real practice, we always have what we call redox couples. We have a reduction, 1 or more reduction reactions, and 1 or more oxidation reactions. And the number of electrons liberated by the oxidation reactions must always equal the number of electrons consumed by the reduction reaction, or we'll begin to get literal electrostatic pushback in the circuit, which will shut everything down. In some cases, we actually take advantage of that concept and do that artificially, and that's one type of what we call cathodic protection, which we'll touch on later in this lecture. So cell potentials complete the circuit. Half cell potentials are great for describing thermodynamics, and they're also useful for describing reaction rates, which are the kinetics of the systems, but you can't have them in isolation. So, as we said, electrons used or liberated from half cell reactions need to go somewhere. We always have to have conservation of charge. So, we always have 1 or more oxidation reactions which liberate electrons, reduction reactions which consume them. The spatial location, the site, the place where we have reduction reactions in a corroding system or a practical redox cell is called the cathode. And the site of the liberation of electrons or the oxidation reactions is known as the anode. And the cell potential is the potential difference of the half cells which make up the anode and the cathode. And we have a schematic down here at the bottom of a piece of zinc corroding in an acid. And you can see that the zinc is acting as the anode, and it is undergoing an oxidation reaction. It's liberating electrons, which flow through that nice conductive metallic zinc to a cathodic site, where hydrogen ions accept those electrons and are reduced to hydrogen gas. Meanwhile, back at the anode, the zinc from which the electrons have been liberated is now a zinc ion that goes off into solution, and we see a net loss in the metal. And a question for later in the lecture is, as this schematic is drawn, is the circuit closed? And can anyone see another process that might need to happen in order to achieve charge balance? So we'll leave you with that thought. Some of you may have gotten it already, but we will come back to that when we start talking about mass transport. Okay, non-standard conditions. We mentioned that most things in practice don't occur in 1 molar concentrations, and life isn't always at standard temperature and pressure. So how do we define a cell potential or a half cell potential when things aren't at standard state? We use a thermodynamic relationship between species concentration and temperature called the Nernst equation, and it is specific to what we can define as a generic half cell. And here it's written with A numbers of moles of an oxidized species, that's species O, is going to accept N electrons and be reduced to B moles of some reduced species R. So our reaction coefficients are A, N, and B. So we have A numbers of moles of oxidized species reacting with N electrons to give us B number of moles of some reduced species. So if we want to know what the half cell potential of that is at some concentration other than 1 molar concentration of O and R, or some temperature other than 298, we use the equation in bold called the Nernst equation. So first we have to know what the standard potential for that reaction is, and typically we'll look that up in a handbook or in the electrochemical literature. Then we'll take the natural log of the actual concentration of our oxidized species raised to the power of that stoichiometric coefficient A, divide it by the actual concentration of our reduced species, and raise it to its stoichiometric coefficient B, take the natural log, we'll multiply it by the actual temperature times the ideal gas constant, and that's just your 8.314 joules per mole per K, divide that by the number of electrons involved in the reaction, add it to the standard condition, standard cell potential, and we have the cell potential, or excuse me, the half cell potential for whatever conditions we wanted, namely whatever conditions of concentration and temperature that we wanted. So this allows us to see what would happen if we have more reduced species or more oxidized species, and it should make sense versus what you've seen in the standard EMF series, the standard electromotive force series, where we ranked all the standard potentials. Just thinking about the way back pressure works on a reaction, if we were to suddenly dump in a bunch of reduced species, for instance, we'd put back pressure on the reaction, and it wouldn't be as thermodynamically favorable. So we would expect to need to apply more potential to drive it forward. And so that gives you an idea of the direction that we would expect it to change. Very important to keep track of your signs here, because everything now has a polarity, and it's important to remember which direction things are moving. So please keep in mind what's positive and negative here. Feel free to look up the Nernst equation if you need to reference it to make sure you have the plus or minus signs correct. And bear in mind that if you flip the R and O in the natural log, you will flip the sign out in front of it because of the mathematical relationship of natural log. So you may see the Nernst equation written in terms of the reaction running in reverse, and that's just fine as long as you flip the sign out front. So important things to remember: concentration of species is going to have a bit of a lesser effect on cell potential because it's a natural log relationship, and that tends to give us less severe than linear relationship, but temperature is a linear relationship. And that will be important if we're looking at calibrating reference electrodes, which definitely follow this relationship for those of you who are moving more into corrosion fieldwork. Real corrosion conditions. So we can use the Nernst equation to impart a bit of reality versus standard cell and half cell potentials by allowing us to look at different concentrations of a reacting species in different temperatures. But there's other conditions that can affect the rate of real corrosion reactions other than just reacting species concentration and temperature. We can have what's called complexing, where we have species that become very, very stable in solution and will therefore tend to corrode faster under those conditions with a solution complexing agent. We can make species more or less energetic and reactive in their alloyed state. We talked about how we can increase the energy of a metal by adding solid solution alloys and imparting some strain energy. Well, that will have an effect on the tendency of that material to corrode. We can form passive films. We can form small layers of ceramics by spontaneous formation of oxides under certain conditions, and those will definitely affect corrosion potential and corrosion current. So generally, under real corroding conditions, the tendency to corrode will be determined empirically, experimentally. Excuse me. And good for us, this is a very mature field. There's quite a bit of data, and you can frequently look up what's called a galvanic series, which is again, the ranked tendency of different metals or materials to corrode, to give up electrons, usually specific to a given environment. So it's usually cited for seawater, since seawater is a rather common corrosive agent in engineering practice. And this is an example of the galvanic series in seawater for several common metals. So you can see platinum is at the top because it tends to have the least tendency to corrode, followed by gold and graphite. These are very noble materials. They tend to not corrode simply because they're incredibly electronegative in practice in these environments. Titanium is next, which may be a surprise because it's a very active metal. The reason that it is up at the top in terms of being least likely to corrode or being inert is because it has a very, very potent passive film. It forms a very tight, adherent, thin oxide that literally insulates it electrically and prevents the titanium metal from interacting with solution. Silver's noble, and then we get into a series of our copper and nickel and stainless ferrous alloys, all of which are essentially noble in practice, not because they're electronegative, but again because they form very adherent, effective passive films. And down, of course, near the bottom again are our non-passivating active metals like zinc and magnesium, which pretty much want to give up electrons all the time, and in fact can be hooked to something else in order to give it electrons if we want to do that deliberately. Okay, we've talked so far just about the potential of electrochemical reactions, so the delta G and the delta V associated with gaining and losing electrons. But if we're designing materials against degradation, what we really want to know is what volume or how many moles of material are going away, because that's telling us how quickly we're going to lose cross-section or load-bearing capacity, or how quickly we're going to perforate something. So the quantity that we need to introduce next is corrosion current, the actual number of electrons that are flowing as a result of these electrons. And in metallic corroding systems, that is literally a flow of electrical current from an anodic site to a cathodic site. Lucky for us, we can actually directly relate that flow of electrons to the rate of loss of material. And so if we have a way to measure that electrical current associated with the corrosion reactions, that corrosion current, we can directly estimate the rate of metal loss. And that is actually frequently done both in the lab and the field. So to get that relationship between current and material loss, we use what's called Faraday's law. And we go back to the stoichiometric coefficients of our oxidation-reduction reaction. And we notice that for our reaction, again, above our AO plus N electrons equals B reduced species, we notice that our reduced species, which would, in this case, if we were driving it backwards to oxidation, would be, say, a solid metal. B and N are related in the reaction. So if we had, say, 2 electrons leading to 3 moles of some reduced species, we'd know if we corroded it, for every 2 electrons that passed, we'd lose 3 moles of metal. So we can use that relationship, and we can use the charge on an electron through what we're going to derive as Faraday's law to relate those. So let's have a real reaction. So under the bold title of Faraday's law, we have a solid metal M, and it's going to give up N electrons to form an ionic species in solution. So it's an aqueous ion now with a charge of N+, so it has a valency of N in the positive because it gave up N electrons. So say we let that go for some time t. So during that time we had A, we're just going to use the term A to represent some number. So in time t we have A moles of electrons, travel from our anode to our cathode site, and in our anode site is where we're losing electrons. So that's our metal, and maybe it's zinc corroding and giving its electrons to hydrogen ions like we have over in the schematic. That could be our metal M. It could be zinc. In fact, that would be a very likely scenario. So we have A over N moles of solid metal reacting to metal ions in aqueous solution in our time t. So we could use the density of the metal in the atomic weight to relate that to the volume of metal lost. So we'd have A over N times the atomic weight of the metal, and that should be WT, not WET. It's atomic weight, not atomic wet, over the density. But remember, electrical current is just moles of electrons per unit time. So if we looked at the volume rate of metal loss, we could say, all right, instead of just having A electrons, we could say, well, that was A electrons in time t, and put our time t in the denominator of that fraction, and then combine the A and the t into an I as a current. And so we end up with the volume rate of metal loss as being our corrosion current times the atomic weight of the metal that is corroding over the number of electrons per mole of metal lost, and that's the stoichiometric coefficients in the reaction, the N up in our reaction, divided by the density. And typically N is known, very well known for each different type of corrosion reaction. We can look up the atomic weight of the metal on a periodic table, and typically density is also very well known. So if we can measure corrosion current some way in the field, or if we can characterize corrosion currents in the laboratory for different conditions that we might encounter in the field, we can predict the rate of metal loss and determine when things have to be taken out of service. Very powerful idea. That's Faraday's law. Well, as nice as it is to be able to measure corrosion current, it's not all that easy all the time. It does require use of some specialized electrochemical techniques. On the other hand, corrosion potential is something that can usually be measured with a wire, a clamp, and a reference electrode. It's a very, very easy measurement to make in the field, as well as in the lab. So it's very nice if we can relate corrosion current and corrosion potential together, because one of them is easier to measure. It's also nice to be able to relate these two together because we can use those relationships to better understand the nature of the reactions that are going on and better understand how to slow them down or stop them in the case of corrosion reactions that we don't want. So in order to do this, we can take a look at corrosion reactions a little bit more like an electrical circuit. And this is something that you'll encounter in a lot of fields of material science where we use concepts of electrical circuits to describe the kinetics of other types of reactions. We saw this a little bit maybe if you've covered viscoelasticity in this course, where we use springs and dashpots to build effectively equivalent circuits to represent flow and elasticity in viscoelastic materials. We can do the same thing with the resistance to charge transfer in a corroding system. Now that resistance has a lot of different sources that we'll go over, but we can lump that resistance to charge transfer and resistance to progress of an electrochemical reaction together into something that we can treat like an electrical resistance. And oddly enough, true electrical resistance is in fact one of those components because of the need for charge transfer in these electrochemical systems. But we can use it representationally for all the other components that might facilitate or impede the reactions that we usually don't want. So we'll go ahead and look at corrosion potential and current in light of what we call the cell resistance. So just dropping back a little bit, we're going to remind ourselves that we have to have charge balance in any kind of redox system or corroding system, and that our corrosion current has two components. Again, now we're looking at completing that circuit. We have electrical current flowing through the solid conductive material. And again, this is why metals tend to corrode. We can have electrons flow from an anodic site to a cathodic site, as opposed to chemical reactions where you still have charge transferring, but it all has to be in the same place. we can have separation of anodic and cathodic or oxidation reduction sites. And that's one of the reasons why metals corrode electrochemically. Now that would be great, but sooner or later you have to have the charge come back. Otherwise we would literally polarize the metal electrically like a capacitor. So in order to complete the circuit, we have to have ionic current flowing through our solution in which this corrosion is taking place. And that's why saltier, more solutions with higher ionic strength tend to promote corrosion. They allow completion of that circuit. So we can look at that circuit. The resistance to that circuit completion is our R cell. So this is just a big resistor. So our cell has 4 very distinct components, and these are things that will require more voltage, more thermodynamic drive to complete them. So you can think of these as series resistors in our cell. So our cell equals R1 plus R2 plus R3 plus R4, and each of these series resistors is symbolically describing a chemical or an electrochemical or a mass transport reaction that has to be driven. So our R1, so to speak, is the limitation on the rate of charge transfer during the electrochemical reactions at the metal electrolyte interface. Just getting those atoms ready to go into solution, rearranging them at the surface, absorbing things, that takes time, it takes activation energy, and so we can represent it as a resistance to charge transfer. It's like a little resistor. Then, not surprisingly, we have to transport reactive species through solution and up to the reacting interface. And we notice that that takes time, and it takes a concentration drive, which we described with Fick's law in our diffusion section. And so we can represent that as a resistor. There's resistance to general ion movement. You can move ions to complete the charge circuit other than the ones you're reacting. You'll hear this termed a supporting electrolyte. And so we have another resistor that's related to that moving. And then, of course, we got to move the electrons through the metal itself. And so that has just a purely electrical resistance. So we can look at a term that we call polarization. And that's just basically describing resistance of the cell or of any component of the cell in terms of just the voltage. So this involves looking at it as if we were passing a constant current and using Ohm's law to describe the relationship between potential and current under those conditions. So if I had a constant corrosion current and I was looking at the cell resistance and said, okay, I'm going to keep passing the same amount of current, but say I did something that increased my cell resistance. Well, Ohm's law would say, hey, you need a higher cell potential to continue to flow that same current, because V equals IR, or delta E core equals I core times delta R cell. So in a lot of cases, since we tend to measure voltage, or we measure E core, we'll describe an increase in cell resistance, which we're usually trying to achieve, in terms of the resultant change in cell potential for a constant current. So it's just an application of Ohm's law, and that's what the term polarization means. It means the increase in corrosion potential, or the increase in potential of a half reaction, if we were flowing constant current as a result of an increase in resistance. So polarization means higher resistance to current flow of any part of a corrosion reaction. So effectively, it's the potential analog to those R1, R2, R3 components of our cell resistance. So we're going to zero in on 3 of those series resistors and describe them in terms of their potential analog. And that's the resistance to charge transfer at the interface, which is called activation potential. We'll look at the resistance to mass transport, very diffusional, so it's described by Fick's law, just like our carburization was, and that's called concentration polarization. And then we'll just look at pure electrical or ionic resistance to charge flow through a solution or through the metal, and that's called ohmic polarization. So starting with activation polarization, this gives a little example of it happening and just gives you an idea of what constitutes it. If we're going back to our zinc and hydrogen 2 half cells, if we look at what is actually required to reduce hydrogen ions, like in an acid, which is pretty simple, to hydrogen gas on something that makes it really easy, like platinum, which is a powerful catalyst. As facilitated as that may be with a platinum catalyst, there's a lot of steps, and you can see that down in the schematic on the lower left. You have a hydrogen ion in solution. It has to actually get from solution and absorb on the metal interface. So that's number one, where the ion in solution comes and sticks itself physically onto the solid metal interface there, and that's called adsorption. Then in a second step, it has to accept an electron coming from the metal. Then now it's not H+, it's just H. It's monoatomic hydrogen. Well, that's not going to form a gas. You need 2 to form a gas. So we have to wait for that same sequence of 2 things to happen to another hydrogen ion. Then you have to combine them, still on the metal surface, to form diatomic hydrogen. Then you have to desorb it, form a surface, and make a little gas bubble. That's a lot of steps, and it takes time. This is kinetically inhibited. And so the time and the activation energy that's involved in all of that can be thought of as a little part of the cell resistance and having its own polarization or its own voltage change if we demanded that that happen at a certain rate or a certain current. So for these types of reaction kinetics, there's a relationship between the driving potential and the resultant current that we get, and it's a logarithmic relationship. So it's E, which is the potential driver, times a constant beta, times log, or natural log with a different B, of the actual current divided by a reference current. It's called the exchange current density, and it's basically the current that would be flowing if we weren't driving the system from the outside, kind of like a little dynamic equilibrium with no net current flowing through the external circuit. So this is another log relationship, and it's frequently referred to as the Butler-Volmer equation, and it just describes the chemical kinetics. But it's a resistor, if you want to think about it, that does not follow Ohm's law. So you can see in Ohm's law we have a linear relationship between current and potential, and here we don't. And for corroding systems, it's important to remember that both the anode and the cathode are going to be subject to this, but it is typically the charge transfer reactions at the cathode that are slow. So a rule of thumb, if you want to stop corrosion, stop it at the cathode. Tends to be more effective. Okay, well, to get that hydrogen in there to react, we had to get it from solution up to the reaction interface. And as we saw when we were carburizing, it takes time to diffuse things. Liquids are a lot faster, but it still takes time to corrode. And quite often charge transfer reactions can be fast if we have catalysts or if we drive them hard. And so in as many cases as not, we end up limiting the rate of reaction by just simply waiting for species to migrate from solution to the metal interfaces. And so we can describe the rate of reacting species transport by Fick's law, just like we did for case hardening. And because these are charged species diffusing, we can assign a current, because a movement of any kind of charged species can be described as charge per unit time, and that's a current. So if we get to the point where every time we have a species, a reactive species, hitting our metal interface and it reacts the minute it gets there, so there's zero concentration right at the interface, that's a condition we call limiting current. And that means the rate of the reaction, or the cell resistance, is pretty much being entirely controlled by the rate of transport of species to get to the reaction interface. And the general term for the increased need for driving voltage in order to overcome this time to diffuse things to the reaction interface is called concentration polarization. And that is something that's very commonly encountered in the field as well. So we might want to look at the relationship for these two different conditions, and we can plot the driving potential, the electrochemical potential, for half-cell reactions, because we'll tend to look at these in terms of differences in anode and cathode. They tend to operate under different conditions. So here we have electrochemical potential plotted on the y-axis. So this is our voltage driver. And then we have current density plotted on log scale down on the x-axis. So that's the current flowing. And in most electrochemical corroding systems, Mother Nature will be setting our electrochemical potential, and then current will flow, and our role as corrosion engineers is to stop that, generally. So if we were looking at our cathode reaction, say we were reducing some hydrogen ions to hydrogen gas because we had an acid and we had some zinc in it, we could look at increasing the current density going from left to right on our x-axis. And if we look at the reduction reaction up in the green, where it's labeled 2H plus 2E minus going to H2, we see that that line slopes down going to the right. So we started at 0, our standard conditions for our standard hydrogen electrode, oddly enough, because we are talking about reduction of hydrogen. And as we demand that that happen at a higher and higher rate, we increase our current for that reaction effectively, we see that the electrochemical potential drops. Well, that's happening with the log scale, so that's where we're seeing that logarithmic dependence here, this E log I over I0. And it would go in the other direction if we forced it to run in reverse. Now we have the same thing going on at the zinc-metal interface. It's giving up electrons and releasing itself into solution as zinc ions. And so if we weren't driving that, we would see that it would be happening at equilibrium with an exchange current density indicated by I0 of zinc over zinc 2 plus at a very low current density, a little bit higher than what we had for hydrogen, but pretty low nonetheless at 10 to the minus 8 amps per square centimeter if you trace down on the x-axis. If we give it a little drive though and increase its potential up to where it meets that of hydrogen, we can see that we can increase the current density by about 4 orders of magnitude. So now at the point that's labeled IC, which stands for I corrosion or corrosion current, we have the current associated with the hydrogen reduction and the current associated with the zinc oxidation the same, which is really important because for a corroding system that has to be true. Otherwise, electrons are going to pile up somewhere and we're going to stop the reaction. So at 10 to the minus 4 amps per square centimeter, those reaction rates are the same, and that system would corrode under those conditions freely. So that's associated with an electrochemical potential or a corrosion potential of something a little shy of negative 0.5 volts and a corrosion current again of 10 to the minus 4 amps per square centimeter. Now if we had the atomic weight of zinc and we knew what N was, which we do from the reaction here, it's 2, we could put that through Faraday's law and see how quickly we were losing a volume or a weight of zinc, and I can tell you that's pretty fast. Now sooner or later something's going to pile up and we're going to be limited by mass transport. And like I said, cathodic reactions tend to be more kinetically inhibited. In this case, it also takes a while to get rid of the hydrogen gas, so we will actually hit limiting current in terms of having to diffuse things in and away for the cathodic reaction here first. So if that were the case, we would get a current potential relationship like we see over on the left. So instead of the cathodic reaction continuing to increase in current density as we drop the potential and give it more and more drive, it's going to hit a point where it just levels off and we get a vertical line, which means no increase in current. That current is constant. And effectively, the potential goes to infinity, because under limiting current, changing the potential does not change the current. It is now independent of potential and is merely awaiting diffusion. So that really changes the relationship when you look at what's happening with the zinc, because now you're going to intersect those two corrosion half-cell curves, current potential relationships, at a different point, usually resulting in a dramatic reduction in the overall corrosion current. Not always so dramatic, but typically that's one way of slowing things down. So again, all that is limiting current plotted as a constant on a log current density versus potential plot, and then plotting our logarithmic relationship between corrosion current and potential, and looking at it for different half-cell reactions. So this is just a way of looking at related rates and understanding what the corrosion current versus potential will be for different corroding systems. Okay, well, as engineers, our general goal is to stop corrosion or to reduce its rate. And one of our best friends in that arena is what's called passivity. Mentioned again that it's the genesis of the corrosion resistance for stainless steels, nickel superalloys, titanium, and aluminum. So what is passivity? It is literally the spontaneous formation of a tight, thin, adherent oxide or oxyhydroxide layer, usually mixed metal, on a metal surface on exposure to a corrosive environment. Typically these are environments that, not surprisingly, have quite a bit of dissolved oxygen. Oxidizing environments, reducing environments make this tough, and that's why quite often you have to go to fairly elaborate, exotic, and expensive alloys when you have to protect them in reducing environments. Just to get an idea of how thick these are, they are usually quite a bit less than 1 micron in thickness. You can't see them. You can hold up a piece of titanium or stainless steel and you can't necessarily see the passive film. Most of them they have to be continuous. Most are electrically resistant. Not all of them, but most of them are. So you can see that they stop corrosion in two ways. They literally physically prevent the solid metal from going into solution, and they also prevent charge transfer across that interface. So they stop both physical migration of atoms into solution as ions, and they also stop that charge transfer at the interface, therefore basically effectively making your activation polarization infinite or very, very high. So if we were to look at how that would look on a current potential relationship diagram, you'd get something like what we see here over on the right. So if we have a metal system corroding, but instead of being zinc, maybe it's stainless steel or it's nickel or titanium, we would start out at equilibrium where we're not driving the corrosion through the external circuit, and you would have our exchange dynamic equilibrium of that metal with solution, and that's the I0 that you see at the little point down near the bottom of the diagram. As we started to increase its potential and drive it in the anodic or oxidative direction, it would follow that logarithmic relationship that we defined for activation polarization. But rather than continuing up along that straight line, it would hit a point where it would suddenly bend over and drop back to the left, indicating a dramatic reduction in current. Because remember, we have current plotted on the x-axis as a log scale. And we could continue to increase the potential and try to drive that reaction harder and harder, and nothing would happen, because effectively we're driving that over an electrical resistor. So we'll get a several order of magnitude drop. Eventually, for most systems, we'll reach a point where if we apply enough potential, we will overcome that passivity and then dramatically increase the rate of corrosion, and that's called the transpassive region. But that's fairly difficult to do, and it typically involves the presence of some extremely oxidizing species that you don't normally encounter. So for most practical applications, we can maintain passivity in definitely typical atmospheric outdoor conditions, seawater, weathering conditions in the out of doors. So that's a potent weapon when we're trying to reduce our corrosion current is introduce a material that can form a passive film. Okay, which brings us to the subject of corrosion rate determiners. If we're looking at a particular system and trying to decide, say, how much money we want to put into a corrosion-resistant material, are we going to need a coating? Are we going to need some electrochemical corrosion mitigation techniques like cathodic protection? Those are all expensive, and some of them don't always work. And maybe we just want to see, what's our rate of corrosion? Maybe we're going to be taking some part out of service before it loses too much cross-section. So we might want to be able to just kind of gauge and estimate what is going to be our metal loss rate, and use that to decide how we'll use Faraday's law to maybe relate corrosion current to metal loss. So these are the factors that are going to basically give you an order of magnitude or more change in your corrosion rates. First, obviously, what material is it? The more active the metal, if it doesn't passivate, the faster it's going to corrode. What temperature are you at? We saw that in the Nernst equation. So you can end up with a much higher cell potential just simply by increasing the temperature. Not surprisingly, temperature has a multiple effect. Most of the kinetics of charge transfer are exponentially related to temperature. So your activation polarization will drop, and your rate of your charge transfer kinetics will rise with temperature. We know from our diffusion coefficients that those are exponentially related to temperature. So if we raise the temperature, we can get reactive species to the interface faster, and our limiting currents are going to rise. Likewise, if we're talking about species transport, fluid velocity will have an enormous effect. If you're used to fluid dynamics, you know that there's a small boundary layer, even in a flowing system, that has to be diffused across. The faster your fluids are flowing, the thinner that boundary layer is, and effectively the faster you'll be able to get reactive species to interfaces. In some cases, we don't have tight passive films, but we can form salts or more loosely adherent corrosion products that are nonetheless protective. But in a flowing system, those can get literally washed away or ripped away, so that can also increase corrosion rate. I discussed complexing agents a little bit as things that will stabilize our oxidized species in solution. These will dramatically increase the rate of corrosion in many cases. Some halide ions will do this, and there are organic complexers that are very potent. Many of them have a dual role in that they will break, literally disrupt, in the solid phase, the passive films that we may rely on in the case of things like stainless steel and titanium. So aggressive solution ions are a big problem. We'll also see that these have a role in stress corrosion cracking and hydrogen embrittlement, definitely the stress corrosion cracking side. So they can have an embrittling role, which goes way beyond simple metal loss. Then geometric effects. I mentioned that we always have to have charge balance. Hopefully I mentioned that a lot. We have to balance the number of electrons being lost by the anode with those being used by the cathode. Well, if we change the relative areas of anodes and cathodes, and maybe we cut the anode down in size by half, that reduced area is now going to have to supply twice the current density to satisfy charge balance. So something we never want to see in corrosion is what we call big cathode, little anode, because that concentrates the current density at the anode and makes the reaction rate occur much, much faster. This can be used actually to advantage in techniques called electrochemical milling, where we use that effect to drill a hole through something. It's seen less beneficially in crevice pitting and galvanic corrosion, which all involve separation of oxidation and reduction reactions and tend to lead to very large cathodes relative to the size of anodes. Which brings us to corrosion types. So the type that's probably the easiest to deal with is what's called uniform corrosion. And this is where we'll have anodic and cathodic sites almost on a microscopic scale distributed all over the surface of a material, right close together, and so you'll always be balancing the size of your anode sites with your cathode sites. This leads to uniform metal loss all over the surface, very easy to predict with Faraday's law. A little bit less nice and less easy to predict is galvanic corrosion, and here's one of our first instances of big cathode, little anode. As you can see, we have a washer that's probably a plain carbon steel or maybe high strength steel. Underneath the bolt head, it's being bolted to something that looks an awful lot like stainless or nickel alloy, which is acting like a gigantic cathode and is actually probably reducing oxygen from the environment, given that doesn't look like it's in an acidic solution. So that entire surface of shiny stainless steel is drawing electrons from that poor corroding washer and releasing it to oxygen reduction as a cathode reaction. So the current density at that washer is very, very high, and as a result it's losing metal atoms and forming corrosion products and going away very quickly. So galvanic couples effectively allow you to increase your cathode area rather than your anode, and they do that by hooking an active metal, which will lose electrons, with a noble metal, which won't lose electrons and will simply act as a big old substrate for some other reduction reaction, usually in our case oxygen reduction or hydrogen reduction. Crevice and pitting. These are the two most deadly forms of what we call occluded cell. And this happens when we don't get enough solution exposure. So they occur when you have bolted lap joints, or you have a little hole, a pit, any time where you have one portion of a material that doesn't get access to solution and the other does, or the majority does. What happens is, in that occluded area that's not getting access to the reducing species, which you would otherwise think is great, it becomes the anode, and it's very small. So it will give up electrons, it'll go into solution, the electrons will flow through that nice conductive metal to the areas that do have contact with the reducing agent, like in this case you can see it's oxygen being reduced to hydroxyl. And so, just as was the case of the galvanic corrosion, that occluded area that's down in the crevice will give up electrons to feed a reduction reaction going on all over the surface of the boldly exposed material. There are other things that happen chemically down in that crevice that keep this going and actually accelerate it. As those metal ions go out into solution, they are actually they have such a high charge density, they will acidify the solution locally, making it harder to passivate and shut down the reaction, and actually attracting, by ionic electrostatic interactions, other aggressive species that keep things going. So corrosion pits and crevice corrosion is often described as being autocatalytic, and it's very deadly, especially if you have something like a pressure vessel or a pipeline that you'd rather not have a hole in. Speaking of deadly, this is probably the worst thing you're going to encounter. Stress corrosion cracking. And if you have already had the lectures or read the topics under material failure, this fits in with the concept of fracture and your K1C fracture toughness. So if you have studied that, you'll know that the toughness of a material is going to be dependent on a material constant and the length of pre-existing cracks. So stress corrosion cracking is a condition under which the material's K1C will drop as a result of its exposure to a corrosive environment and its own tendency to corrode. There are a lot of different actual mechanisms by which this happens. Film breaking at a crack tip of a passive material, absorption of aggressive species at a crack tip. These are all going on at the atomistic level. Won't go into them, but the important thing to remember is you need a susceptible material, a pre-existing tensile stress, and the unique environment that makes it susceptible. And there's some classics. Halides like salt for austenitic stainless steels, and ammonia for any kind of copper and brass. So quite often, just the residual tensile stress in a material from, say, some kind of heat treatment or cold work will be enough to kick these off. If you are designing something for fracture and you are looking up a K1C, be warned. Stress corrosion cracking will reduce those K1Cs by 2 to 3 orders of magnitude in days from initial exposure of that material to the aggressive environment. There's even a special name for the K1C in these aggressive environments, and that's K1SCC, meaning fracture toughness in the mode 1 crack opening direction under stress corrosion cracking conditions, K1SCC. You'll actually see that in the literature. So these are very important to remember, and they're luckily well documented. It goes under material selection. And unfortunately, you can get the same situation happening when you're pumping electrons in, especially for steel. So this is the cathodic version of fracture toughness loss or environmental embrittlement. It's called hydrogen embrittlement. Hydrogen is a tiny, zippy little species, and it can get into crystal lattices, and it can prevent dislocation movement, just like we discussed in our defects section, and this causes a material to become very brittle. This is particularly problematic because we can encourage this to happen by applying cathodic currents, which we otherwise do to prevent corrosion. This is one of the means of corrosion prevention that we'll get to. And so, oddly enough, in an attempt to prevent stress corrosion cracking, we will often apply what's called cathodic protection. And if it's misapplied, we can actually take a material from being susceptible to stress corrosion cracking to being susceptible to hydrogen embrittlement. That's something we can manage, but it's important to be aware of it. Hydrogen embrittlement tends to be mainly a problem for high-strength steels, and your susceptibility is proportional to your yield strength. So materials that you'll quench and temper, heat treat up into very, very high strengths, things like tool steels, they're very susceptible, as are maybe highly cold work materials. And again, this is more of a problem with steel than it is with our non-ferrous. Okay, how do we stop all this? Corrosion mitigation. First, best way, proper material selection. Use an alloy that is resistant to the environment. Then you don't have to worry about applying coatings and cathodic protection. Pick something that's going to work in the environment. Usually a passivating alloy, or if you really need to, go with a non-conductor. Go with a ceramic or a polymer if your other material requirements allow. If you can't do that, go with a coating. Keep that surface environment from touching your metal. In a lot of cases, an organic coating will work. Paints, fused epoxies, these are all great for room temperature environments, especially weathering environments. Ceramic coatings work very well. Sprayed oxides, baked enamels, etc. You just need to make sure that they don't have any holes or what's called holidays, where you can actually get higher rates of corrosion through those. We can apply a sacrificial coating. That's what zinc galvanizing does, or aluminum coatings quite often. So we can electroplate or hot dip our steel with a layer of zinc, and then in addition to preventing contact of the corrosive environment with our iron, the zinc will tend to give up electrons which will flow into the iron and protect it. So that is a zinc galvanized coating is a very effective locally applied version of what we call cathodic protection, because something is applying electrons to our structure and rendering it the cathode, making it the cathode. If we have a closed loop system like a heat exchanger, we can reduce the rate of charge transfer at the interface by adding special chemicals which absorb on the interface and prevent charge transfer on that microscopic level. So that would be driving our activation polarization. These tend to be somewhat nasty. We don't want them out in the environment, so we would only typically use those in a closed loop system. Furthermore, if they're not replenished, their concentration at the interface will eventually decline and they'll become less effective. So really great option for the right conditions. And then, as we mentioned, in reference to like a zinc coating, we can apply cathodic protection, which has a lot of general applications beyond just zinc coatings. And in all cases, what it involves is making the thing we're trying to protect, the structure, we're making it the cathode of a larger cell. And there are lots and lots of ways of doing that. And so we just have one slide which shows it really quickly. There's two main types of making something a cathode. We can bolt it to something with a much lower electrochemical potential, a more active metal like zinc or magnesium or aluminum. And that active metal will corrode, it'll give up electrons, it'll go out into the environment as an ion, and then the electrons that it gives up will run through a wire or conductive strapping that you're connecting to your structure. It'll flow into your structure will then be the cathode, and it will polarize in a direction that will tend to make it passive and reduce the rate of corrosion, if not stop it altogether. If we don't want to use a sacrificial metal or we need much higher currents, we can actually use a current source, a rectifier, or a battery, and we can drive electrons from an inert reaction like a big piece of graphite or a big piece of stainless steel that we also bury in the ground with our structure or put in the water with our structure. Obviously we have to be completing our ionic circuit and then literally pump electrons into our structure that we're trying to protect. And of course, if we're pumping electrons into something, it becomes the cathode, and so it will not tend to want to give up its own electrons. So if we have to use a current source like a rectifier or a battery to put electrons into our structure to make it the cathode, this is called impressed current cathodic protection. And if we are worried about hydrogen embrittlement, that's the one that we will have to manage carefully, because if we pump those electrons too hard, put them in too fast, then we can get hydrogen embrittlement. And that's actually something that has been extensively modeled and protected against, no pun intended. And you might, depending on which course you're taking, have done that as an exercise for diffusion. Okay, polymers. Wow, they're non-conductive. How are they going to corrode? Well, they corrode their own way. First and foremost, remember most polymers are non-polar, so with the exception of nylons or things that have polar side groups or polar molecules in the main chain, a lot of polymers are non-polar, things like polyethylene, polypropylene. So if we had a non-polar solvent like an oil or something like cyclohexane or an aliphatic hydrocarbon solvent, it might just want to migrate in and sit in there next to those nice non-polar chains. And if it did that, it would swell it, and those chains would have higher mobility, they'd slip past one another, and before we knew it, we'd have yield and creep and lots of degradation in mechanical properties. Likewise, if we had, say, a nylon, like nylon 6,6, that has quite a few polar groups spaced close together, we might have water migrate in and be associated with that and swell it. So those are two cases in which we would have the environment interacting with our polymer and degrading our properties, even if there wasn't a direct breaking of the chemical bonds. So that's swelling, and so that's reduction in properties by reduction in the secondary bonds associated with polymers. And not surprisingly, this is definitely more of a problem with thermoplastics because it's held together with secondary bonds. Now, if you get a very aggressive environment, things like peroxide radicals, for instance, that you can get from photooxidation, which we're going to hit next, we can cleave those main chain bonds, and we can cleave the covalent bonds that are holding together a thermoset polymer, a network polymer, if we get an aggressive enough environment. And if you're picking polymers for use in chemical service, not weathering outdoor environments, but hopefully closed reaction vessels where you might be encountering very, very oxidizing species, that can be a problem. Things like hexavalent chrome, ferric chloride, and species like that are powerful oxidizers can actually start breaking your primary bonds in your strong polymers. So that can be an issue. Speaking of which, you can get that outside. We have a note to dissolution, which again is just simply the end result of extreme swelling. if you don't have chemical crosslinks, obviously if you swell a polymer enough, you can totally separate the chains, in which case you have a solution, which might be good if you're going to do GPC to find molecular weight, but isn't so good if you're trying to hold something together. It's also the basis of solvent welding. Again, thermoplastic problem only. And again, that dissolution is like swelling. It's relying on overcoming secondary bonds. But if we're looking back at disrupting our primary bonds, we had mentioned that up till now, from the last slide, it took a pretty powerful oxidizer to do that. We can also do it with light. Ultraviolet radiation has a high enough energy to break the main chain of a lot of different polymer species, especially aromatics, which unfortunately are some of our stronger polymers and are used for structural applications in things like Kevlar, some of our high-strength fiber polymers. So in this case, we literally have a photon coming in and cleaving either a side group or a main chain bond, and you can imagine that if we're cleaving the main chain, every time we do that, we cut the molecular weight in half. So that is a process called photolysis, direct lysing or direct cleaving of a bond. Even if we don't cleave a bond, we can, under the action of light hitting our polymer molecule, we can create very, very aggressive oxidative species, mainly peroxide radicals being a big problem with polyethylene. And now we're back into the same situation we were with the strong oxidizer degradation, and those strong aggressive species can then go on and cleave our main chain bonds. So this is unfortunately fairly common with polyolefins, polyethylene, and a lot of our engineered plastics. So these are susceptible to photooxidation, if not photolysis. And so this creates a rather bad situation where the very materials that we were using in the out of doors to be protective, because maybe we didn't want to have to deal with electrochemical corrosion of metals, are now being degraded by exposure to light. And again, there's always ways to engineer around this. We can put in absorptive pigments that basically absorb the light and prevent it from reaching polymer further down. We can put in additives that will absorb the photooxidative aggressive species. We can put multiple layers on. There's a lot of ways to deal with that, but we do need to be aware that it happens, especially if our polymer is being used directly in a structural application. But secondarily, if we're relying on it, say, as a paint or a coating to protect something underneath, it won't necessarily last as long as we think it does. Okay, these yellow slides are bonus slides that I will not talk through in this particular lecture, but if you're going the route of material science, if you're an engineer, if you're particularly interested in corrosion, or if you're going more the chemical synthesis route into polymers, these are the underlying concepts that are used to derive things like the Nernst equation and the Butler-Volmer equation. They make the jump between relationships like concentration and reaction potential to chemical potential. These are your basic thermodynamic relationships. So if you were looking at taking a more advanced class and wondering where the material up till now in this lecture fits in with what you may be learning in a physical chemistry course or an inorganic chemistry course, here's where you're making the link. So these are the thermodynamic relationships between species concentration via activation, chemical potential, and how they would actually fit into the concept of electrochemical potential and the derivation of the Nernst equation from that on the basis using charged species. And you can put that together and actually build yourself your very own electrochemical cell potential using your fundamental thermodynamics there and go through that. And you do end up with a Nernst equation. And it's a lot of fun, and it's an exercise you will go through possibly if you take physical chemistry. So it's a good highlight for those going in that direction. So we have some credits here of where some of the references came, the Callister text and a few other sources that are fun to check out if you're interested in corrosion. But that is the lecture for today, so hopefully you're more aware of what's going to happen to all of the great materials that we're designing once we put them into service, so that they will last in the intended application. We will see you next time.